Hello everyone, this is William John Holden. It's been a while since I've put up any code, mostly because I haven't been coding much lately. I've been taking a class, mostly off but partly on, of course, in algorithmic design and techniques with edX. It's been a good class. I've enjoyed it. I will say that if you already have a degree in CS and you're not able to do a master's, then this is a good option. Other good options would be Euler Project and Advent of Code. So I wouldn't say that this is the best possible thing to do, but it's very affordable and it's been a lot of fun. Now, a problem that I'd like to explore, and I'm not going to give away my solution because that would be unethical and all that, but one of the problems that they had us look at is the partitioning problem. So given... changed my screen and everything looks crazy. So here you can read the problem description for yourself, but given a set, you want to find three subsets such the sum for each of the three subsets is equal. So this really caught my attention because I've actually worked on a project similar to this in a completely different context. My application was physical fitness. I wanted to create teams for relay races that were as fair as possible. So unfortunately, this turns out, I had tried a relatively naive, greedy approach, which gets you to a good enough solution really easily, where you just start at the extremes and work your way in. But this is not a perfect solution, and in many cases, there won't be a perfect partition. But it turns out this is an NP-complete problem. I was able to solve this using depth-first search, which was not recommended by the course material, but I thought it was pretty interesting. So my program has gotten pretty gnarly, and I don't want to show off the source code, which is why I'm making a video, because again, I don't want to be, academically unethical, but here's what it looks like, though. I wrote a program to visualize it in OpenGL, and so what you're seeing, if it's red, that means that's not a solution. If it turns green, then that was a solution. Now this is intentionally not using a minor optimization where, well, I shouldn't say minor. So when you do this, you should be going through, you're iterating through a lot of possibilities, but you don't have to come back. So notice here, when we're going, I think that this input right now is the numbers, it says at the top, integers 1 through 9. So this is probably 1, and then it probably goes up to 2, and then 3, and et cetera, and you can see how it's iterating. And in this case, it's iterating through all possibilities over all three spatial dimensions. Now, you really don't have to do that. If number 1, once we've tried 1 in the x direction, there's really not a reason to try it in the y direction with the other 8 possibilities still floating out there. So that's an observation that we can get to a solution a little faster than the full. I assume this is going to be, now that I think about it, I don't know, 3 to the 8th, 3 to the 9th possibilities, probably 3 to the 9th. So that's a lot, and we don't want to. We really don't want to go to that extreme, but 3 to the 9th. So we don't want to evaluate that many, and this program is brute forcing it. It's going to try all of them, and we can construct a dynamic program that, again, if 1 doesn't work for x, 1's not gonna work for y. So you can use the short circuit OR operator to kind of fail fast, and so there's a lot of room for optimization there. But this is it, and this is how it looks. The insight the reason that I'm creating this video is I had this insight, is that you can look at the three-way partition problem geometrically. And that's what you're seeing here. So hopefully this is extremely intuitive when you see it, that if the line turns green when x equals y equals z. Otherwise, it stays red. It's not a solution. So this geometric approach, I think is really, I don't know, it was my idea. I thought it was clever, and it works. There's probably a better solution out there, but hey, there was one. But yeah, so interestingly, I found with the dynamic program, although there was some room for improvement, I didn't feel like there was tons of room for improvement. Namely, you could find a positive solution really fast, but if there is no solution, then you may have to iterate through kind of a lot of them or all of them. My actual submission didn't make any effort to. So there's kind of some obvious things that you can do. You could do something like, say, sum the whole set and see if that's divisible by 3. If it's not divisible by 3, then a solution is not possible. You might be tempted to look to shrink the problem space, but this doesn't really work. For example, say you're given a set and you're going to try to find a partition of 1, 1, 1, 6, 9, 9. So it might have been tempting to take away the 1s. So let's say we do like 3, 4, 5, 6, 7, 8. So 8 and 4, oh no, 8 and 3 is 11, 4 and 7 is 11, 5 and 6 is 11. So in this case, it would have been okay to remove the 3s, but in this case, it would not have been safe to remove the 3s. So that optimization is something I looked at and just through a single counterexample demonstrate that it's not a safe choice. So this is it. I mean, this is how I spent my day, and hooray. But I thought this was a pretty fun little program to write. I hadn't written any OpenGL code in a long time, and man, I don't miss it. Like, I don't know. Maybe it's just me, but I find OpenGL to be a bear. But anyways, I hope this is interesting. Oops. Didn't